In this video, I'm going to be talking about the International System of Units, also known as the metric system. Short SI coming from the French, which is how I'm going to refer to it. SI is a system that has 7 main units, being time in seconds, length in meters, mass in kilograms, electric current in amperes, thermodynamic temperature in Kelvin, amount of substance in moles, and luminous intensity in Candela. I will be explaining all of these, also how to read these SI unit configurations, so hopefully at the end of this you'll understand everything there is to know about the SI system. The SI system was created to have units to be able to describe anything using these units and units derived from them, because out of combinations of those 7 main units you can literally create any other unit you can think of. And these units you can trust. They're all defined by physical constants of the universe, so they will never change, and the goal of SI is for these units to be able to be used forever to describe everything. So let's go over these 7 base units. First of all, time and the second. The definition of the second is how many times a cesium-133 atom switches between 2 states. Let me explain. Cesium-133 has an electron spin of 1/2 and a nucleus spin of 7/2. Every particle in an atom has a certain spin. In the case of cesium-133, most of the neutrons' and protons' spins cancel out, and the ones that don't give the nucleus a spin of 7/2. The electrons also have spin, and they come out to be 1/2. Now, if the electrons are spinning in the same direction and are aligned with the nucleus, the spin of the nucleus and electrons will add up to a total of 7/2 plus 1/2, which is equal to 4. Let's call this energy state F is equal to 4. If they aren't aligned, F is equal to 7/2 minus 1/2, which is 3. F is equal to 3 is a lower energy state, but if we give the atom energy exactly equal to the difference of F3 and F4, then it will swap to the F4 state. It will then emit the energy and fall back to the F3 state. The energy getting absorbed or emitted happens in a fraction of a second, being 1/9 billionth of a second. So theoretically, this can happen 9.2 billion amount of times per second, or it has 9.2 billion hertz. Since hertz is the definition of cycles per second, once 9 billion of these cycles are done, 1 second has elapsed, which is the definition for the second. Next, length and the meter. The speed of light is the fastest any object with a non-negative mass can travel. It is, so to say, the speed limit of the universe. In order to move something, you need energy. The more mass an object has, the more energy you need to move it. But photons, that is the particles of light here at the bottom, have 0 mass. So this is what it would basically be like if you added infinite energy to the box at the top, which has mass. It would travel at the same speed that a photon travels at, which is the speed of light, which comes out to be 299,792,458 meters per second. I am sorry for the bad explanation, it's bad because I came up with it. 1 meter is defined as the distance light travels in 1/300 millionth of a second. And yes, this is really the definition for 1 meter. It's not so much that the meter is based off of the speed of light, but the speed of light is based off of the meter. Same with seconds and that piece of cesium-133. Also, the second can also be defined using the speed of light, so yeah. Next, mass and the kilogram. The constant defining the kilogram is the Planck's constant. First, what is Planck's constant? Well, Max Planck was working on a problem in thermodynamics. You see, there's a problem at the time. Imagine a black body, which is an object that absorbs all electromagnetic radiation, no matter how it comes in contact with the black body. The object doesn't give off any energy except for the energy as thermal electromagnetic radiation. The graph describing this radiation is a spectrum of wavelengths which are related to intensity, which are dependent on the temperature. Just let that sink in, look at the graph, I'm sure you can understand it. Basically, before Planck, People thought that the shorter the wavelength of emitted radiation would be, the higher energy it would have. This would catastrophically lead to the ultraviolet waves having infinite energy, which obviously isn't possible. So Planck fixed this by adding his Planck's constant, and now the energy would peak at a point but would go down as the wavelength decreases. By the way, this is the function describing this graph. With his constant, he could create this function, thereby fixing the problem of short wavelengths having infinite energy. The Planck's constant would later be used to describe the energy of a photon, which has no mass, so we calculate its energy via its frequency. That is, the energy of the photon is equal to the Planck's constant multiplied by the frequency of the wave of the photon. Now, all of this to explain why the Planck constant is related to mass, and the definition for the kilogram. Why E equals mc squared, we know that mass is just a different way of saying energy. If we now take this formula, we can divide both sides by the speed of light squared and get the mass of, well, we can just get the mass. If we now say, for example, we have a photon with a frequency of 1, this would basically turn into the mass is equal to the Planck's constant over the speed of light squared. And this is why the Planck's constant is used for mass, because it kind of describes it. I do have to say though, I know not much about this topic, so please correct at all points if you think something I said is wrong. Also, I'm not saying the definition for the kilogram here, because 1, I will go over all the definitions of all the units later, and 2, just get ready to deal with this. Next, electric current and ampere. As always, we'll start with the constant. That is the elementary charge E. E is the electric charge of a proton/electron. They have the same charge, just proton is positive and electron is negative. This charge is absolutely minuscule and comes out to a tiny amount of coulombs. Now the base unit of electric current in SI is the ampere. So what is an ampere and what is a coulomb? An ampere is the flow of charge per second and the coulomb is the amount of charge. Here's the math. The coulomb is ampere times second and the ampere is coulomb per second. The coulomb is the quantity of electric charge carried in 1 second, with the current being 1 ampere. So the coulomb is the charge itself, like for example in elementary charges, and the ampere is how many coulombs travel past 1 point per second. Coulomb per second, the flow of charge. Imagine a wire. This wire has an electric current of 1 ampere, meaning that 1 coulomb is traveling through it per second. 1 coulomb is about 6.2 quintillion electrons, so this wire, with an electric current of 1 ampere, would have 6.2 quintillion electrons traveling through a point per second. The ampere is the flow of electrons, the electrons moving from left to right, and the coulomb is the amount of electrons themselves. Thermodynamic temperature and Kelvin. Heat. Heat really is just atoms moving. Depending how quickly they are moving, that determines the temperature. By the way, if they stop moving completely still, this temperature is called absolute zero, which is what the Kelvin is based off of. It starts off from 0 Kelvin being absolute zero, the point where atoms do not move at all and are completely still. The constant for thermodynamic temperature is the Boltzmann constant. So what is the Boltzmann constant? The Boltzmann constant is a tiny amount of joules per Kelvin. Let's just digest that. Kelvin is temperature, and you don't even need to know what joules are. Joules are energy. And while I was researching online, I stumbled upon this. It's more of a historical annoyance than anything else. Temperature and energy might as well be measured in the same units, but traditionally they never are. Both could be given as joules, or both could be given as Kelvin, but the convention is that energy is in joules and temperature is in Kelvin. Thus, we need a conversion factor for joules per Kelvin. That's the Boltzmann constant. It's as if someone decided that the length of a straight line should always be measured in inches, and the length of a curved line should always be measured in centimeters. Then you would need a silly constant, something like 2.54 centimeters per inch, which would appear, for example, in the formula of the circumference of the circle. And yes, this person is correct, but I don't want temperature and energy to be the same thing. Let me explain to you why. Because when you really think about it, if you want to measure the movement of atoms themselves with huge amounts of energies like joules, you're going to get tiny amounts of joules. For example, we can literally use the Boltzmann constant to calculate how many joules something like, for example, room temperature, that is right now in the summer, 30 degrees Celsius, 86 degrees Fahrenheit, or 303.15 Kelvin would be. Since the Boltzmann constant is joules per Kelvin, if we multiply the Boltzmann constant with the room temperature, we get the amount of joules. This is a minuscule amount, and when we put this into the smallest form of energy, electron volts, so we can get any scope of how stupendously small this is, I just lose my mind. For context, the mass of the particle with the least amount of mass ever discovered is measured in electron volts. The particle with the smallest non-zero mass ever discovered, the electron neutrino, which before its mass's discovery we thought it was massless, has a mass of about 0.8 electron volts. And now for the big reveal, the room temperature we just calculated using the Boltzmann constant, we just converted to joules, and now electron volts comes out to be about 0.026 electron volts. 30 degrees Celsius comes out to 0.026 electron volts. And not gonna lie, I would rather use Celsius than fractions of electron volts to describe that I am dying of heat in my room. So I am a bit happy we didn't use the variables we do for energy for temperature. But yeah, this person is very correct. The Boltzmann constant is still dumb. Next, amount of substance and the mole. So I don't know, this might be the dumbest one. A mole is literally just a number. It's just a big number, no units, just 602 sextillion. That's it. And the Avogadro constant might just be the second most useless thing after the mole. What the Avogadro constant is basically a mole divided by a mole, which is 1. Now you might be thinking, what's the point? And that's a great question. The point of the Avogadro constant is just to say that there is a mole amount of substance per mole. For every mole, there is a mole amount of parts. Really amazing, isn't it? The definition of the mole is the amount of atoms in 12 grams of carbon-12. And to end it off, luminous intensity, probably the least known. What is luminous intensity? First, the units and constants. We'll just work backwards. So there are 3 things: Candela, lumen, and lux. Basically, the human eye is most sensitive to light when it has a wavelength of about 555 nanometers, being the color green. Scientists came up with a function to describe the brightness of light based on the wavelength, with, as I said earlier, 555 being the peak. This function changes though, based on how well lit the scenery is. If it is a bit darker, the peak decreases in wavelength by a little. Anyway, luminous intensity is the measure of light by a light source on an angle based on this function. And Candela measures this intensity. So a candela is the luminous intensity by a light source in units. 1 candela is roughly equal to the light emitted by a candle. Also, funny thing, the light a candle emits actually has its own name and is called candle power. How exciting. Anyway, while the candela is the power, the lumen is this power over 1 steradian. Basically, on a 2D circle, it has 2 pi radians. So a radian is an angle of 57 degrees. This, which causes a 2D angle, in 3D is called the steradian. And yeah, that's all it is. Steradian is just a 3D radian, creating a 3D area. A sphere has 4 pi steradians. So if we were to have a light uniformly lighting up all its surroundings with 1 candela, that would have 1 candela times 4 pi, which would be equal to 12.57 lumen. Now a lux is a lumen over a square meter. So a candela is the luminous intensity, a lumen is the luminous intensity over the steradian, and a lux is this luminous intensity over a square meter. If you were to measure lux, you would be measuring how much luminous intensity lands over the square meter. No matter if it's Candela, Lumen, or Lux, the more it is, the brighter it is. The difference is Candela and Lumen measure how much gets emitted by a light source, and Lux measures how much lands on some area. Good example is the sun. The sun has 2.2 times 10 to the 27 Candela. Yet if you're standing on Earth directly under the sun, there's only about 32 to 100,000 lux landing on you, or the square meter you're standing on. The constant defining the candela is luminous efficacy of 540 terahertz of radiation. And this actually isn't even that complicated. Luminous efficacy is just how well a light source produces light per energy, in this case watt, that goes into it. When considering a monochromatic light source at 550 terahertz, this constant comes out to 683 lumens per watt. Mono meaning one and chromaticus from Latin meaning related to color, so a monochromatic light source is a light source emitting only one color. This emitted color has a frequency of 540 terahertz, which is a wavelength of slightly more than 555 nanometers. And the constant is 683 lumens per watt. So yeah, that about covers that. And basically, out of these 7 units, you can make any unit. Any and all units are possible, explained in this next section, that is math. You see, until now, I've been doing the normal thing, the not SI thing. But now, if you go into any unit and look at the SI definition, you will not find division signs. You see, quite obviously, and I think everyone knows this, if 2 variables are next to each other, they get multiplied. But what might confuse people at first is that when you see, for example, speed, velocity, meters per second, it wouldn't be written like this, but like this. Basically, whenever something is exponentiated to the negatives, that means it's divided. So this would mean meters per second, meters divided by seconds. If the exponent is positive, that just means exponentiation. If it's negative, that means divided by the exponent that is there. So this would be, as I said 50 times before, meters per second. If we do this, though, this would mean meters divided by second squared, or acceleration. And the larger the exponent, the larger blah blah blah, you understand. Also, if the first variable in something is to a negative exponent, the whole thing is then divided. For example, hertz. Hertz is cycles per second, how many times something happens per second, or seconds to the negative 1, which is the same as 1 divided per second. So 60 hertz would be 60 times per second, because one cycle happens every 60th of a second. And also, you will sometimes have prefixes before units, and we all know what they are. Very simple, just look at this and let's move on. So let's now explore some well-known units and some not well-known. So first, I'll start with the Newton. The Newton is kilogram times meter over seconds squared. What this means is that a Newton is equal to the energy needed to accelerate 1 kilogram by 1 meter. You can also calculate Newtons like this. This is literally just a different way of writing famous equation, F is equal to ma. Force in Newtons is equal to mass times acceleration. We can split this in 2. One is mass, the other is acceleration, and that's it. That's how simple it is. Let's make it more complex. The joule is just the force that a Newton does over 1 meter. But there's a different definition for it, being coulomb times volt. How do these two come out to a joule? Well, let's open these two up, and we find out that a coulomb is this, and a volt is this huge thing. But when we multiply this together, the ampere and second from the coulomb cancel out, giving us a joule. Isn't that something? And if you remember at the beginning, I mentioned all of these base units are based off physical constants. So let me explain that. The definition for the kilogram is this. That is the Planck's constant multiplied with the cesium energy switching, the value is 9.2 billion, divided by the speed of light squared. In SI units, this is this. And now from this, how do we get kilograms? First of all, we can simplify. This second here multiplied by 1 over second is the same as second divided by second. which is the same as divided by second squared. So now that we've cleaned that up, it's looking much better. To get rid of that meter over second squared, we can multiply by its reciprocal. You see, if we have something like A over B divided by C over D, like we have here, if we switch C and D around and multiply instead, we get the same answer. In other words, if we multiply any number n that has been divided by C divided by D with the reciprocal of C over D, meaning that they switch the numerator, the number at the top, and the denominator, the number at the bottom, around, that is D over C, we get the same answer. That applies here. In our case, this is n, and the bottom's C and D. We get rid of C and D at the bottom by multiplying by its reciprocal, turning this into this, something we can work with. When we have fractions being multiplied by each other, if the units diagonally or vertically are the same, we can cancel them out, because that's just how it works. This turns into kilogram times meter, which isn't really a thing, so this just turns into a kilogram, and boom, from this silly equation to a kilogram. I'm not going to cover the things in the middle and the bottom, just the top left, because that is enough. Basically, these things have values, so in order to come out to 1 kilogram, and not like 10 quintillion kilograms, they get multiplied by its reciprocal, and whoa, would you look at that, we just explained all of the units. Yeah, that is honestly all it is. For every base unit, the definition is n1 over n2 multiplied by n2 over n1, which always, no matter what n1 or n2 is, comes out to 1. And that is basically it with my video. I will explain all of these definitions, but if you don't care about that, then that's it. Thanks for watching. Anyway, let's move on with the meter. This one's really simple, and using the reciprocal again. This is meter over second over 1 over second. We multiply the reciprocal, that is s over 1, which is the same as second. Meter divided by second multiplied by second is equal to meter. Boom, SI definition of meter speedrun. Next, second. Actually, same exact thing here, except not at all. 1 divided by 1 divided by second. Reciprocal 1 multiplied by second, 1 second. Not that deep. Also, here I will mention everything else. If you look at it, the definition of a second is just 9 billion of these energy state switches of cesium. So really, a second isn't based off of the constant, but the constant is based off of the second. This is the same with everything else because, duh, if we were to really base this off of some constants, then the base units themselves would change. And so for example, a second would be much shorter. That's why every definition is based off of the unit itself. Next, ampere. This is cesium constant times elementary charge. Elementary charge is in coulombs, which is ampere times second. And second divided by second cancels out, and we are left with 1 ampere. Next, the Kelvin. This is Planck's constant times cesium standard over the Boltzmann constant. The Boltzmann constant is joules per Kelvin, but we can't forget joules isn't a base unit. It is equal to this. Now, simple, same thing as always. We multiply by the reciprocal, which makes it this, and we simplified the left part by just dividing by the second. These two terms are equal, so we can cross them out and we get Kelvin. I don't even want to talk about this. Mole is the dumbest thing in science. I've seen it in a while. Same thing as I said earlier in the video. The definition is this. There are 1 mole amount of parts in a mole. Next, Candela, which is this. Planck's constant multiplied by cesium constant squared multiplied by this constant. Now this is what it comes out to. And the Candela constant is 683 lumens over watts. Now, lumen is Candela over steradian, but the definition for steradian in SI units is meter squared divided by meter squared, which is 1, so that doesn't matter. Now, what is joules per second? So it's the same thing as Planck's constant, the only difference being that it's not that at all. What turns into this, and now we can cook. So these two can be simplified, coming out to a watt. Then we cross these out because it's the same thing and we are left with 1 Candela. How exciting. Now, I've hopefully taught you something, and also, This is the metric system that we use today in science. Whenever you come across some formula, they're using these units. With SI, you can get all units. How nice. Except decibel and fon or neper. Also, if you want, you can check out the website metricsystem.net to go look at some things I didn't cover. For example, how to write and say these units correctly. Honestly, this is pretty cool because I learned I do some of these things incorrectly. So see if you do too. Also, if you